It's a pleasure to have all of you here for the special section on dynamical systems and ODEs. Before we start, I would like to mention maybe a not very well-known aspect of the personality of Wellington de Mello that unfortunately passed away recently, and a person that we dedicated this special section. And the character of Wellington include also generosity with the development of mathematics in Brazil, including regions deep inside the country where he visited and stimulate young people to produce mathematics. So I would like to if you allowed me, to dedicate this section also to Wellington de Mello. I would like to introduce Professor Laura DeMarco from Northwestern University. Professor Laura graduated at Harvard University, where he finished her PhD. And he's gonna gift us with a talk about complex dynamics and arithmetic equidistribution. Thanks.
Thank you. Thank you very much. It's certainly an honor to be here. And I'm delighted to see so many of my friends here in the audience. Thank you for coming. So what I'd like to talk about is a certain connection between complex dynamical systems and aspects of number theory, specifically arithmetic geometry, that has seen a lot of development over the last 10 or so years. A lot of people are working on connections between these subjects. And I'd like to highlight some of the connections today. So my goal in this talk is, well, there are three parts, really. The first is to describe a notion of arithmetic equidistribution that can mean many things, but the notion that I have in mind is one that was introduced by Szpiro, Ullmo, and Zhang more than 20 years ago in the context of studying abelian varieties, the arithmetic and geometry of abelian varieties, defined over number fields. And the connection, which is the arrow, this one, to complex dynamics, and specifically how we've used these arithmetic equidistribution results in complex dynamics, where there we're studying maps that are not algebraic necessarily, that are, or rather not arithmetic, and, that are defined over the field of complex numbers, but how we've still been able to use the algebraic techniques on the left-hand side to obtain new results about complex dynamical systems. So I'd like to explain that bridge by an example, and then at the end of the talk, I hope to come back in the other direction and explain some more recent results that I've been involved with, some projects where we're trying to use, or we have used, results in complex dynamics to return to that original setting of abelian varieties and the geometry and arithmetic there, some open questions that were left 20 years ago that we've been trying to work on. Okay, so that's the plan for this talk. But to bring this setting a little bit down to earth, what type of complex dynamical system am I talking about? For this talk, I will exclusively talk about dynamics on the Riemann sphere. So holomorphic maps of the Riemann sphere are very simple. They're just rational functions, ratios of two polynomials. For interesting dynamical features, such as beautiful Julia sets, we assume that the degree of the rational function is at least 2. So the maps are not invertible. So this is the type of dynamical system I'll be talking about today. So to define the other word in my title, or the words, the arithmetic equidistribution, let me just explain what I mean by equidistribution first. Here, this just refers to the notion of a collection of points in a space that are uniformly distributed in that space with respect to some natural measure. And the measures in question here will typically be something related to the dynamical system. So just very generally here, I'm typically working on the Riemann sphere. So I have some compact metric space, some given probability measure, which is natural to the setting. Equidistribution just means I have a sequence of finite sets that are growing in size, and as they grow, they become distributed according to that measure. So just putting equal weight on each of the elements of that set and letting n grow to infinity, and these discrete probability measures should converge to the given measure. So that's just the notion of equidistribution. Okay, this slide is illustrating what I would consider to be the most important example, or one of the most important examples of equidistribution in the context of rational maps on the Riemann sphere. So this is a result, oops, wrong button. Okay, so this is a dynamical equidistribution statement, which, so the setting here is we're working on the Riemann sphere. Again, I have a rational function of degree at least 2. The measure now is, so the natural measure to consider here is the unique measure of maximal entropy. So these systems have a unique measure of maximal entropy. This was proved in the early 1980s. And the support of that measure is exactly equal to the Julia set, the chaotic locus for the dynamical system. And one of the equidistribution statements that one can make about this measure is that the periodic points are uniformly distributed with respect to that measure. So it's, I mean, these are just rational functions. It's easy to see that if you fix the period, there are only finitely many periodic points. You can compute the number of them. It's growing as the period grows. And these, it turns out, will become uniformly distributed with respect to that measure. But it's not just the periodic points that are uniformly distributed. Lots of other important sets for the dynamics are uniformly distributed with respect to that measure. For example, as I've written here, also preimages of points. There are some exceptions that we understand, but outside of a few exceptions, if you take any point in the sphere and look at its preimages, then as you go backwards in time, these preimages also become uniformly distributed with respect to that same measure. So this is an important, fundamental, I would say, example of an equidistribution statement in the context of in these dynamical systems. Okay, but arithmetic equidistribution, what do I mean by arithmetic? So for this audience in this dynamical system session, I imagine most of you are not familiar with height functions, but the context is the following. So what I've illustrated on the top of the slide here is the definition of something called the Weil height function, or logarithmic height function, which is a function, a real valued function defined on the algebraic numbers, or in general, the algebraic points of some variety. So here I'm defining it on the non-zero algebraic numbers. I'll talk about the definition more in a moment, but one of the properties is that it's measuring, in some sense, the arithmetic complexity of an algebraic number. So it's non-negative, and it's 0, so the minimal complexity, or the 0 points, it turns out, are precisely the roots of unity. So these are the algebraic numbers that are considered to be of minimal complexity. They have height 0. And all the other algebraic numbers have positive height. The height function is unbounded on the set of algebraic numbers. The equidistribution statement that I will read is a statement about the geometry of the points with low complexity, the geometry of points of small height. Okay? So the statement, again, before I go back to talk a little bit about the definition, the statement is that if you take any sequence of algebraic numbers, non-repeating, just to avoid trivialities, if you take any sequence of algebraic numbers with height tending to 0, which is the minimum value, or perhaps height equal to 0, that's okay too, but height tending to 0, and if you put discrete measures uniformly distributed on the algebraic number itself and all of its Galois conjugates, then these measures are converging to a natural measure associated to that height. And in this case, that natural measure is precisely the uniform distribution on the circle, on the unit circle in the complex plane. So for this particular Weil height, the natural measure is the uniform distribution on the circle. Okay? So it's a statement about the geometry of algebraic numbers with low complexity. But let me talk about the definition itself, because it's relevant for what I want to talk about today. So if you haven't seen it before, so an algebraic number, of course, by definition, is a root of a polynomial with integer coefficients. So if you take the minimal polynomial, so what I've written here, suppose a0 represents the leading coefficient, the height is defined in terms of a quantity with the size of that leading coefficient, and then a quantity that measures an average of the size of the roots of that polynomial. So, of course, the algebraic number alpha itself is a root, and all of its Galois conjugates are precisely the roots. But you only consider the roots that are outside the unit circle. So you just record the Galois conjugates that are big, you take some average of their size, and this records what's called the height. This is actually expressed, there are many ways to write down the definition of this height function. This particular expression is just 1 over the degree times this is the Mahler measure expression here. In any case, this is the object which satisfies this property. It's 0 if and only if the algebraic number is a unity. By the way, this definition reduces to something quite simple in the case of a rational number. If you have just a ratio of 2 integers, you just look at the largest of the numerator and denominator, and that gives you this quantity, which is the height here. Okay, so again, the equidistribution statement is a statement about this height function, which is defined on the set of algebraic numbers. In this case, it's a set of non-zero, but typically we just say h of 0 will be 0. We may as well make that height 0. And so it's a statement about, again, the geometry of the algebraic numbers with low complexity, of small height. But the key thing that I want to emphasize about this statement is why this particular measure is the one to arise, why the uniform distribution on the unit circle is associated to this height function. And it's exactly because of this. If you take a look here, that function that I wrote, the log of the max of the absolute value, is precisely the potential in the complex plane of that distribution. So if you just take the Laplacian of that function in the sense of distributions, in the usual way, you get precisely this distribution, which is uniformly distributed on the circle. And that's no accident. One could very well replace this particular subharmonic function on the plane with some other, your favorite continuous subharmonic function on the plane that grows like the logarithm near infinity, and produce another height function, a brand new height function, and one would obtain, by modifying the existing proofs of this theorem, one would obtain corresponding equidistribution theorems. And there are lots of modifications that can be done in this way. It doesn't have to just be modifying this piece. One could also modify this piece. And that was done about, 12 or so years ago, generalizing this particular theorem of Bilu from more than 20 years ago now by a whole series of authors. Actually, there are a few different proofs of this, but the basic idea is there's this whole collection of height functions that one can consider on P1, on the algebraic points of P1, or on the algebraic numbers themselves, which are required to satisfy certain hypotheses, but the basic input is to take that log of the absolute value of x that I had in my definition and replace it with some other subharmonic function and obtain what I like to call a good height. So a height that satisfies certain reasonable hypotheses, and one gets the same kind of statement, that if you take the small points, if they exist, not every choice of function is going to even have small points, but if you have a sequence of points whose heights are tending to 0, it will always be the case then that degrees of those algebraic numbers are growing to infinity, so the Galois orbits are growing, and those orbits will then be equidistributed with respect to the associated measure, which is nothing more than the Laplacian of that function. Okay? So this was formulated by, again, a whole collection of authors at this time, and there are some technical definitions for the notion of good that I'm not going to go into, but if I have time later, I might say a word about. And these types of equidistribution statements have been generalized greatly. Of course, it's not just about functions on P1, but in a much more general context. Okay, so this is the notion of arithmetic equidistribution that that this talk is about and that we've been using to prove certain results in complex dynamics. So now is this sort of second part of the talk. I want to, this was just some examples. Let me just skip that and move on. In the second part of the talk, I'd like to explain how we've used, just an example of how we've used this type of equidistribution statement to prove results in complex dynamics. Again, I'm just going to show a particular example. But again, how to obtain results really about dynamical systems defined over the complex numbers, not just those that are defined over algebraic numbers. So here's an example question. I call this a warm-up problem. It's just sort of for fun. It's not anything too profound, this particular statement, but let's just take a look. What's the question? Here I have the family of quadratic polynomials, parameterized as usual by C as a complex number, z squared plus c. So this is the most famous, the most well-studied family of dynamical systems on the Riemann sphere. And the question here is, suppose you take two elements of this family, so two quadratic polynomials, how many common periodic points can they have? Or common pre-periodic points can they have? Remember, these are not invertible dynamical systems, so points can be pre-periodic and not periodic. So the question is, how many points in the plane can be pre-periodic for both? Can there be infinitely many, for example? And how might we answer that question? So again, pre-periodic just means finite orbit. Okay, are there only finitely many? So how do we investigate a question like this? Well, the first thing we might look at is, where are the pre-periodic points? Where are the periodic points? Well, in complex dynamics, we know very well that the Julia set is filled with periodic points. They're dense in the Julia set. I mean, most of the pre-periodic points here you're going to find them here at the boundary of this black set. This illustration, this is for a particular example, and the boundary here is the Julia set of that example. So you would expect to find lots of periodic points on the boundary of that black set. In fact, you do. And so if you take two different examples, for example, c equals 0 and c equals -1, and you intersect those two sets, well, they do have some intersection, although it's not totally clear how much intersection there would be. So it's not completely clear from the picture if there would be an infinite overlap or a finite overlap, or if that overlap could even take place where the points happen to be periodic or pre-periodic. But just playing around with the examples, the geometric approach, just looking at the intersections, probably won't get us very far. If you take two parameters that are very close, then often their Julia sets will look very similar. And so this is an example of two parameters that are fairly close, superimposed upon one another. And you can see that it's hard to tell. It looks like their boundaries might have lots and lots of overlap. Here's another example where their boundaries really do have lots and lots of overlap, so it's not clear. Let me show you the actual Julia sets. On the left, you see in blue, dark blue is supposed to represent the Julia set for this parameter, -1.5, and on the right, the Julia set for something sort of nearby, and their Julia sets intersect the real interval in lots and lots of points, so you might expect their intersection of the Julia sets to be big. So it's not obvious from a geometric point of view whether to expect the periodic or the pre-periodic points to have overlap or not. Okay? That's one more picture with two different Julia sets overlapping in lots of places. But the theorem for this particular family of examples, which uses equidistribution, is the following statement, that in fact, they never have an infinite overlap unless they're the same. So if you take two quadratic polynomials, if they're not in this family, if they're not the same, then the intersection of those infinitely many periodic points is always going to be finite. And this was proved by myself with Matt Baker, and independently at the same time by Xinyi Yuan and Shouwu Zhang. And so I want to illustrate how the proof goes. It's not hard. I should be able to explain the whole proof in just a couple slides as an application of equidistribution. So here, the theorem is repeated, that if I'm looking at this family of quadratic polynomials, two of them share infinitely many pre-periodic points if and only if they're the same. Now, I've formulated it as an if and only if statement. One implication is well known. If they are the same, then, of course, it has infinitely many periodic points. This is a well-known fact in complex dynamics. And here's an illustration on the slide of just one example where I've plotted a bunch of periodic points. Okay, so there's nothing to say there. What we really want to say is if they share infinitely many preperiodic points, how do I know they're the same? So we break it into two cases. First, if the parameters happen to be algebraic, then we can apply the tools that I was talking about. So first, we consider one of these good height functions on P1, on the algebraic numbers. And that good height function actually has existed already in the literature for many years. This is what's called the canonical height for this dynamical system, which is nothing more than, well, this little h here is the V height. So this is just looking in the way we always do in dynamics at the growth rate of some given quantity that we're interested in. In this case, we're looking at this growth rate of the usual height along orbits, and that defines the limit, it turns out, exists. That was proved in this article, and that turns out to define the canonical height. This idea actually goes really back to Tate in the 1960s, who used this idea in constructing the canonical height for an elliptic curve defined over a number field. And this height has the property that its zeros are exactly the preperiodic points, the ones we're interested in. So then, once you have the height, the theorem is essentially an immediate corollary of equidistribution. Because if the two maps have infinitely many common preperiodic points, those are height 0 for each of them, then that set, it turns out is Galois invariant, not for the absolute Galois group necessarily, but for some number field which is large enough to contain both A and B. So you get this Galois invariant set of preperiodic points, which will then, by the equidistribution theorem, have to be uniformly distributed with respect to the measure for FA, but also for the measure for FB. So in other words, the measures are the same. Okay, so just to emphasize, the advantage of the arithmetic equidistribution theorem over the one that was known in the complex setting, we knew that all the preperiodic points were uniformly distributed with respect to the measure of maximal entropy. But this arithmetic version says it's also the case when you look at infinite sets of Galois invariant subsets of preperiodic points. So you don't need all of them for uniform distribution, as long as the set is Galois invariant. Okay, and that's what you get here. And then from some complex analysis, from some complex dynamics, it's known for this particular family that if the measures are the same, the maps are the same. Okay, so that's an illustration. But what about the complex parameters? This is, again, just for the algebraic parameters. For the complex parameters, and this is, by the way, I should say, the passage from the algebraic case to the complex case was really one of the main points of these articles, which is something we were trying to illustrate in that particular article, which is not so hard to do once you know what to look at. And the idea was simply to say, if the parameters are not algebraic, so they're transcendental over Q bar, one can still use these same types of heights, the same notion of canonical height. It's just that the underlying fields are no longer number fields. They're not finite extensions of Q anymore. We have this finitely generated field. We have, in this case, we can view it as a function field, where A can be viewed as some sort of parameter. So you have a height function defined in that setting, and one can do the same thing. There's still an equidistribution theorem that holds in that context. The only subtlety here is that equidistribution is not in the space you started. It's not on the Riemann sphere anymore. It's not on the Riemann sphere, at least not a priori, although it could, we know equidistribution holds when you have all of the preperiodic points. But in this case, what happens, and I'm going to avoid the technicalities, but what you do get is equidistribution holding on a whole sequence of spaces of Berkovich analytifications of the P1 with respect to each of the non-Archimedean absolute values that we put on this field. Okay? So what we get is an equidistribution theorem that holds on a different space, a family of auxiliary spaces, but at the end of the day, one makes the same conclusion. One can deduce as a consequence that the sets of pre-periodic points are the same. And so for these examples, that guarantees that the maps are the same. That's not true in general for rational functions on the Riemann sphere, but for these functions, it is. That if you know just the set of pre-periodic points, then you know the map itself. Okay, so that was just to illustrate, again, this idea of using arithmetic equidistribution, which is introduced in the context of studying objects defined over number fields, and then taking it, extending it to a question that could work over in the complex setting. Now, one can generalize these types of statements in many different ways. There are lots of things one can say. I mean, of course, there's no need to restrict ourselves to this family of quadratic polynomials. There was almost nothing in my proof that was really related to quadratic polynomials except that final equality. But you get a different conclusion in other contexts. But there is one generalization that I'd like to talk about, which I have to say, I've put an X on it. We very quickly exit the realm of warm-up problem when asking other types of questions that are related to this. And one key question one could ask is, well, how many pre-periodic points do these things have in common? Now that we know we take two different maps, they have only finitely many periodic points in common, or pre-periodic points in common, well, how many can there be? Can it be as many as we wish? And so it turns out for this family, however, the answer is no. And this is some brand new work of mine together with Holly, Krieger, and Hesse-Yi, where we've shown that for this particular family, one can strengthen this finiteness statement to get a uniform bound on the number of common pre-periodic points for two different maps in this family. There's a uniform bound that we call M, so that the number of common pre-periodic points for two different quadratic polynomials of this form is bounded by M. And again, this is over all complex pairs, A and B, that are distinct, of course. And so I would like to say just a few words about the ingredients of the proof, because it's still using this arithmetic input. It's still using arithmetic equidistribution and height functions, but in a slightly different way. But before I do that, I'd like to also say something about the motivation. I said the arithmetic equidistribution theorems themselves came from the context of studying abelian varieties or elliptic curves. And so the questions that we're asking have also evolved. And a lot of the questions are also coming from questions in the context of studying, in this case, elliptic curves. I'm doing one-dimensional dynamics, so it would be the corresponding questions would be the one-dimensional abelian varieties, which are the elliptic curves. And this particular question was inspired by a conjecture, a recent conjecture of Bogomolov, Fu, and Chinko. But there's a long history of questions of this flavor. In fact, maybe I should say, even this question was truly inspired by a lot of questions in arithmetic geometry that go under the title of unlikely intersections. And there's a long history of those that I don't have time to talk about. But let me at least mention what this conjecture was, which is in parallel to this statement that we've been able to prove. But in order to state that conjecture, let me first explain the connection, which is very elementary, in fact. The connection between studying torsion points on an elliptic curve and studying pre-periodic points for a rational function on the Riemann sphere is very, very simple. If you take any elliptic curve, just complex torus with some distinguished point as the zero, there's this natural quotient down to P1, which is just the identification of a point with its additive inverse. So it's this 2-to-1 quotient. And if you take then an endomorphism of your elliptic curve, which is not an automorphism. So let's take, for example, this one, multiplication by 2 on the elliptic curve, which will exist on any elliptic curve. So we could use this one in families if needed. It will descend. So starting with an endomorphism up here, it will descend to a morphism of P1 down here. And in such a way that torsion points on the elliptic curve become precisely the points of finite orbit downstairs. So studying counting problems related to sort of torsion points here can be translated into statements about pre-periodic points for this particular class of dynamical systems. Of course, not all rational functions down on P1 arise in this way. There's a very special collection of maps down on P1 that come from elliptic curves. In fact, they're special. They're so special they have a special name. We call them lattice maps, after Lattice, who studied them about 100 years ago. So this very special collection of maps done on P1, by studying those, we can get some insight into some questions about elliptic curves. So this connection between torsion and pre-periodic is just from the definitions, just the very fact that this map descends. So there's nothing deep there. But the conjecture that I mentioned, which I just learned about in a recent preprint of Bogomolov, Fu, and Chinkel, although I should mention that I just asked Yuri Chinkel about this because I didn't know the history of this particular statement, and I understand that it was formulated already 10 years prior in a previous article of his with Bogomolov. But the statement here is the following. So the conjecture is, there's a uniform bound M. I formulated in the same language as the theorem that I was talking about. There's a uniform bound M, so that if you take the torsion points on two non-isomorphic elliptic curves and project them down to P1, their intersection will consist of no more than M points. For any pair of non-isomorphic elliptic curves, working over the complex numbers. So for any pair. And let me remark that in contrast with the dynamical example that I was talking about earlier, these are dense sets of points now. The torsion points here are dense on this torus, and the projection of those points is dense on P1. So unlike the geometry of the Julia sets, where maybe you could try to separate them in some way, these are really, we're looking at the intersection of two dense sets on the Riemann sphere and trying to understand their overlap. Via the correspondence that I mentioned on the previous slide, about torsion points here being exactly corresponding to pre-periodic points downstairs, this statement is equivalent to the following conjecture. So one could say that they've formulated this dynamical conjecture. There's a uniform bound M, so that the number of common pre-periodic points is bounded by M over all pairs of these non-isomorphic lattice maps. Again, working over the complex numbers. And one can restrict to the lattice maps that come, sorry, I didn't emphasize this, but if we consider exactly this example, multiplication by 2, that has topological degree 4, the rational functions down here will also be degree 4. So this is a particular family of degree 4 lattice maps. And so this conjecture is equivalent to looking at that particular family of degree 4 lattice maps and saying if you take any pair which are not conformally conjugate, they should only have at most M pre-periodic points in common. Okay, so this is the statement. This is still open. We have not proved this statement. And the statement that we were able to prove, not for this family of lattice maps, but, let me finish my sentence at least and then come back to this. Sorry, the statement that we did prove was the corresponding version for these quadratic polynomials. There's an important remark I have to make. So it is known that if you take, so the uniform bound is not known, but if, of course, you take any pair of elliptic curves, of non-isomorphic elliptic curves, then it is known that that intersection is finite. Again, we don't know the uniform bound, but we do know that the intersection is finite. And this was first observed in that previous article that I had mentioned of Bogomolov and Chinkel from 10 years prior for elliptic curves defined over Q bar. And I should just mention that the techniques that I already described to you in the dynamical context, the passage from Q bar to C, applies here perfectly well and gives exactly the same statement of finiteness for the elliptic curves over the complex numbers. So exactly the same ingredients that I've already described to you show that for any pair of non-isomorphic elliptic curves over the complex numbers, we know that this intersection is finite. And again, the question is the uniform bound. Do we have control over uniform bound? Well, I certainly believe this conjecture. I'm quite sure it's true, and in fact, we are actively working on it right now, though I'm not ready to announce that it's true yet. But what I do want to show on this slide, just to mention briefly, are some of the key ingredients in the proof of the uniform bound for the dynamical setting, which are not special to the quadratic polynomials, which are the kinds of statements that should carry over to the setting of lattice maps or elliptic curves. And so this slide just shows a few of the ingredients. So the key thing that we study is, well, these height functions that I've already mentioned, and specifically, if you have two dynamical systems, again, you construct the canonical height, sorry, I should say first treat the algebraic case. Assume that the maps are defined over Q bar. And for each individual map, we look at its canonical height function, which is this good height that has the property that the periodic and pre-periodic points are height 0. Now, there's a pairing between height functions of this type, between good height functions, that goes back to Arithmetic, and for the types of heights that we're looking at, it was actually formulated by Zhang, so we call it the Arithmetic-Zhang height pairing. It's actually an intersection number. I didn't say, but so these heights that we're looking at, so I described them just as functions on P1 or functions on the set of algebraic numbers. One should really interpret them as metrics on a collection of metrics on line bundles over a collection of spaces, one associated to each place of the given number field over which you're working. So really, the height function here on P1 is equivalent to the data of a certain adelically metrized line bundle. And these line bundles can be intersected. And so there's a computation that one can do to compute an intersection number. And that intersection number has some very nice properties. In particular, it has the property it's non-degenerate. It's non-negative and non-degenerate. So that you'll get that the pairing will be 0 if and only if these heights are actually equal, assuming that they're normalized and good, and there are various hypotheses that one needs to check are satisfied, but they are definitely satisfied in these dynamical settings. So in fact, here is a simplified, I don't know how simple this expression looks, but this is a definition of that pairing in this setting. In general, there are some other terms one has to include in the definition, but since I haven't defined these terms, maybe it doesn't matter anyways. But just to emphasize what goes into it, this is a sum. So if you fix a number field that contains A and B, one takes a sum over all of the places, over all the different p-adic or Archimedean absolute values that one puts on that number field. And one sums a bunch of integrals. And what these integrals are related to the equidistribution theorems that I mentioned at the beginning. The measures in this integral are precisely those uniform distributions associated to the height. I only talked about the one over the complex numbers, on the Riemann sphere, in particular the Archimedean place. But there's also one for each p-adic place that appears. So you have a whole collection of measures associated to each dynamical system. And these lambdas here are what we call local height functions, but for those of you in complex dynamics, you would be very familiar with the escape rate function for this dynamical system, and that's all that is an escape rate function defined with the v-adic absolute value instead of the usual absolute value. But in any case, it's some collection of integrals, and maybe we can't compute them exactly. We don't know what kind of values we get precisely, but we can estimate them. And that's the way the game goes, is that we provide estimates on these pairings. And one of the key estimates is a uniform positive lower bound on these pairings, which was the first thing to give us evidence that there might be a uniform positive upper bound on the numbers of common zeros. Now that wasn't enough, because it's not true in general that if you pair height functions, if you have a family of height functions with a uniform positive lower bound, It's not true that you get uniform upper bounds in general. One can construct height functions that would show that that's not true. But nevertheless, then one can get a little bit more control on these pairings in terms of the heights of the parameters themselves and in terms of the numbers of common preperiodic points. So that really, the work, it goes into these estimates that give us upper and lower bounds on this pairing. And that's what this project is about, and it was really a study of these pairings and these height functions. Once you have a uniform bound over Q bar, the passage to the complex numbers is formal and is not new. It wasn't something that we had to figure out on our own. Okay, so that was just to illustrate some of the ideas that we expect or hope will carry over to the setting of lattice maps and elliptic curves, but that's for future work. In the last 6 minutes, I want to talk about what I said was the third part of the talk, which was the arrow in my opening slide that pointed back to the left. So if you recall, I had arithmetic equidistribution and abelian varieties on one side of the slide, complex dynamics on the other. I've explained how we're using arithmetic equidistribution in the setting of complex dynamics. This slide is an example of some work from last year to illustrate how we were using these ideas from complex dynamics combined with equidistribution to address some of the unanswered questions about abelian varieties. And this is just one example, and there's a long history, again, that I don't have time to talk about, but let me at least just read the statement. So there was this conjecture. Oh, wrong slide, wrong button, I mean. Okay, there we go. So actually, exactly 20 years ago at the ICM, Zhang gave a lecture, and in his proceedings article, he formulated a conjecture, which was an extension of the work that he had talked about at the ICM. He formulated a conjecture about families of abelian varieties that are defined over a number field. And it's what could be called a Bogomolov conjecture in families. I will say a little bit about the history of this, but let me just go through the statement. A quick remark, what I've written here is a simplification, really just a special case of the conjecture that appears in his proceedings note. But the statement here is, suppose you have a family of abelian varieties where the fiber dimensions are bigger than 1, and assume that the base is a curve. Okay? And everything's defined over a number field. And we fix some line bundle, which induces the narrow and Tate canonical height on the fibers. So on each fiber, we have the canonical height. So we have some sort of height function defined on the algebraic points of this big variety A. And the question is, what is the geometry of the small height points? Is roughly speaking what the question is, which is exactly what equidistribution is built to study. The question here in this special case is, suppose you take a section of this family. Again, assume that it's algebraic, assume that it's defined over some number field. So here's our section. When can there be sequence of points on this section with small height, with height tending to 0, or with height equal to 0? When can there be infinitely many points on that section that have arbitrarily small height? What does that imply about the geometry of the section itself? And the conjecture is that, well, typically you won't expect to see small points on the section that you construct. Typically, you expect to pass through only finitely many height 0 points, which corresponds to torsion points on these abelian varieties, or small points. And the conjecture is that that's exactly the case, that in order to pass through lots of small points from the complexity point of view, that section had better be very special. Special has a precise meaning. I'm not going to go into it, but it just means respecting the subgroup structure of this family of abelian varieties. If this family is trivial, suppose they're all the same abelian variety, then this is known. This is precisely it follows from, well, it's a special case of what's called the Bogomolov Conjecture, and which was proved by Ullmo and Zhang independently, I guess published 20 years ago, or actually I'm not sure if I have that date exactly right, but published approximately 20 years ago, which used the equidistribution theorem that I started off by mentioning, motivating the rest of the talk. And it itself is an extension of what's called the Manin-Mumford conjecture, which was proved by Raynaud in the early 1980s, and which is a statement that if you take a subvariety of an abelian variety, which has a Zariski-dense set of torsion points, that subvariety is special. It must be a subgroup, a sub-abelian variety, or a torsion translate of that subgroup. So that only happens in a special situation, and this is the small height version of those statements, which are known for one abelian variety and have been known for some time now, and this is the family version. It's still open. This conjecture is still open. The height 0 case in families was only just resolved in the last couple of years. Actually, maybe just last year, I suppose, the preprint was completed. By Umberto Zagner, David Masser, they completed the case, as I formulated here, of not small height, but height 0. So the height 0 case is now known, and so the question is, well, suppose you have a sequence of small points, not necessarily height 0. Can we still conclude that that section is special with respect to the geometry of this family of abelian varieties? So the theorem I wanted to mention is that, well, at least in the case where these fibers split as products of elliptic curves, then we know that the answer is yes. The only possibilities for sections that have lots of small points are precisely the special ones that are coming from subgroups of the family. So it's when, well, okay, let me not try to give a definition. I have 7 seconds. It's counting down in front of me. And so the answer is yes in this case. And the final slide, 0 seconds left, is just to list some of the other ingredients that go into proof that I don't have time to talk about. So that's all.
Questions or comments?
It's terrible. So the truth is that right now, we don't have an actual number. There's exactly one place in the proof which is not effective, which I think can be made effective, but the number we'd get from our estimates is probably terrible. It's probably billions, I don't know. I believe that the best number is probably on the order of 10 or something. I actually don't know. I've never seen an example of 2 quadratic polynomials that have lots of common periodic or pre-periodic points. Yeah, well, I didn't work too hard on this, but Holly found an example with 5 in common, and I haven't seen any more beyond that. So it could very well be that 5 is the best one can do. That would be a surprise, but who knows? I genuinely don't know. Yeah.
So if you take 3 or 4 intersections, A1, A2, A3, so could it be 0? Or?
Yeah, so if you want 3 different dynamical systems to have any periodic points in common, that would be absolutely unexpected. So I wouldn't expect any at all. Except unless you, well, there are some, sorry, that's wrong, what I just said. But it would be quite rare. It would be very few, like maybe 1 common pre-periodic point or something at infinity. Or, it would be some sort of obvious construction. But I don't know. The answer is I don't know, is perhaps what I should say. But it would certainly be unexpected.
What are the expected values of A and B for which you get the
Yeah, he's asking if there are particular A and B pairs where we should expect to look for some maximal intersection. Again, I don't know the answer. Presumably ones that have some kind of extra symmetry, if there's some setup with some geometry that one could use to explain it, but I truly don't know.